Hey everyone, this is Abby. I just wanted to go through number 16, the last problem of recitation worksheet number 15, because I know this one was kind of intense, had a lot of different parts to it and a lot to keep track of. So I figured I would go over this problem. I am going to break it up into two videos, one where we're just going through writing the rate law expressions for each step in the mechanism, and then a second one where we go through all of the algebra and substitution of all of these equations. So feel free to watch either or both, take a break in between, whatever you need to do to help you get through this problem. So we'll just get right into it. When we're approaching these types of problems with mechanisms and rate laws, there's a couple things that we want to keep in mind. And probably the most important one is identifying what our rate determining step is. And that's always going to be the slowest step. In this case, our slowest step is this bottom one here. So we're just going to label that as our rate determining step. So this is our most important one. And this slow step isn't always going to be the last step in a mechanism. It could be the first one, it could be one of the reactions in the middle. It doesn't matter where it is, but there's typically only one slow step, and that's what's going to determine our overall rate law expression. So we're going to write the rate law for this reaction first. And there's a couple reasons to do that. And the first is because we want to make sure that there's no intermediates in that rate law. And we also want to make sure that there's no products in our rate law. So if you'll remember from earlier in the worksheet, our overall chemical equation is 6A plus 3B goes to 6C plus 2D. So we want to make sure that when we're writing our overall rate law, that we only have reactants in there. If there's intermediates or there's products in the overall rate law, then we're going to have to do those substitutions and a little bit of math out on our worksheets. So that's why we typically start with writing out the rate law for the slowest step. So that's what we're going to do. And it's going to have the general form of the rate, and sometimes we write it as this curly V, is equal to some rate constant. So for this reaction, that rate constant is K5. And then it's going to be multiplied by the concentrations of each of the reactants. So that's A times the concentration of E. And what we notice is that we have two concentrations in our rate law. One is A, and that's a reactant in our overall chemical equation. So that's totally fine. But then we have the concentration of E. And we were already given in the word problem that E, F, and G are intermediates. So they should never be in our rate law. Just like products like C and D also shouldn't be in our rate law. So that's why we have all of these other faster steps so that we can find the rate laws for those equations and use them to substitute into this last one and get rid of E. And while we're doing that, we're going to generate some other intermediates and products in the rate law. So that's why we're going to go ahead and write all of the rate laws so that we can use them in different steps of our substitutions. So one more thing to note before we write these is that you might have noticed that all of these fast equations have these funny looking equation arrows. And what that means is that there's a forward and backward reaction. So the forward reaction is denoted by the top arrow, which is pointing from the left to the right. And the backward reaction is that bottom part of the arrow. So what that means is that the forward and backward reactions are sort of happening at the same time. They're competing against each other, and they're also in equilibrium. So when we have equilibrium reactions, we have this sort of rule that says that the rate of the forward reaction is equal to the rate of the backwards reaction. So that's how we're going to set up our rate laws, because each rate law is going to have the same form as this one on the bottom for the rate determining step. It's going to be a rate constant times the concentrations of the reactants. So if we write the rate of the forward reaction, the rate constant for that is K1, and that's going to be multiplied by A. And then we have this coefficient out front of A, so that's going to become our superscript in our rate law equation, and then the concentration of F. And now there's nothing out in front of F in the chemical equation, so we assume that's 1, which means the subscript or the superscript would be 1, but typically we don't write that. We can assume that if there's nothing there, it's just a 1. And so now this is the rate of the forward reaction. We're going to set that equal to the rate of the backwards reaction. So that's going to have a rate constant of K minus 1, because now we're going from the right side of the equation to the left side. So now what once was the products of the forward reaction are now the reactants of the backwards reaction. So our rate constant K minus 1 is going to be multiplied by the concentration of C times the concentration of E times the concentration of G. So that's the rate law for the first equation, or the first step in this mechanism. And we're not going to worry about rearranging it at all. We just want to write the rate laws for each of these steps first, and then figure out how we need to rearrange them in the next video for the substitution steps. So we're going to go on to this second equation. And again, it's an equilibrium one, so the rate of the forward reaction has a rate constant K2, and that's going to be multiplied by the concentration of A and the concentration of B. And now we're going to set that equal to the rate of the backwards reaction, which has K minus 2 as the rate constant, and C is the reaction, because now we're going from the right side to the left side, which is the backwards reaction. And then again, same thing for this third mechanism step. We have a rate law K3 for the forward reaction. The reactants are on the left, and it's just A, but we're going to put it to the second power because of that coefficient 2 out front there. And then that's going to be equal to the rate constant for the backwards reaction, K minus 3, times both of the concentrations of reactants, C and D. And then finally, for our last fast mechanism step, we have the forward reaction, which has the rate constant, K4 times B, and now this does have a superscript, just like our previous rate law expression, because there's a 2 out front of B, so that's going to be B to the second power, and it's going to be multiplied by the concentration of G. And then we're going to set that equal to the entire backwards reaction, which has a rate constant K minus 4 times concentration of C times concentration of D times concentration of F. And so now we're done. Those are the rate laws for each of these individual steps. So if that's what you were most concerned with or confused with during our recitation on Tuesday, then you don't have to watch the next video, but you're more than welcome to if you struggled with any of the algebra or substitutions, or just rearranging the equations. So I'll leave that for you all as well. But otherwise, feel free, take a break, grab a drink of water, take a breather, and then I'll meet you back for the second video.